Is the same time as I make this video, so there may be some pauses. Alright, so looking at number 13. We must finish in the top 5. So if you read through this scenario, how many different possibilities of people just qualifying for the next round, not getting first, second, third, fourth, and fifth? This is one that's actually a combination problem because of that. So when we notice that we're just advancing to the next round, how many different ways can we do it? It doesn't matter if you get first or fifth, okay? So here's the deal. I have 12 that are possible, and then I'm picking 5, okay? So what does this come out to? Hopefully I can show you here in just a second. But, well, calculator is not firing up here. There it is. Okay, so how to do this on the calculator? Remember, you can just type it in, but don't forget there is a menu. Then we can go up to, sorry, we got to get to a calculator page first. This is not working very fast for us here, but menu. You can go to your probability page, or probability menu, and then you can go permutations or combinations straight from that. Or you could literally type in what you see there, NCR. But when we're in there, we always put 12 first, the bigger number first, because, excuse me, that's what we're choosing from. And then we have the comma, 5. So when we fire that all out, that's where we get the 792 for the answer for this problem. Okay? So then the next one here, we're holding auditions for the roles of Rudolph, Donner, Blitzer, and Dasher. 32 actors. How many ways to cast them? Well, here's the deal. We're casting the roles here. We're not auditioning to move on to the next round. So really, you got 32 choices for Rudolph. But once you establish Rudolph, now you got 31 choices. And then 30, and then 29. That's the same thing as you saying, hey, this is a permutation. The order, the arrangement, the assignment matters. It's not just order that you got to think of. The assignment of roles matters. And I'm choosing 4. Okay, and if you do this one by hand, you will see that that's the same thing as 32 times 31 times 30 times 29. Okay, and when we fire that all in our calculator, whether we use it like this or we go like this, that's where we get that large number, and that number is 863,040 there. Okay? All right, how many different 9-letter words can be formed with Cleveland? Yeah, baby, Cleveland rocks. Okay, sorry, but Cleveland is the word. Now, this is where I need you right now to focus in on this. There's other problems that are just like this one. They were on our quiz, and it's like, I want you to think about this. I'm arranging letters, but some of the letters are the same. If I did not have, repetition of letters, if I didn't have any letter repeat, this would literally be 9 factorial, because I'd have 9 choices, 8 choices, 7 choices, 6, all the way down. But this problem is unique in the fact that, all right, C is good, but I see 2 L's. Since I have 2 L's, then if I switch these L's, think about that right now. If I just switch these 2 L's, it still says Cleveland. There's not a different word there. So whenever we have that, we see how many times they repeat, and we put 2 factorial in the bottom. The E's, same thing. So I got to put another 2 factorial in the bottom. The V is good. Already did the E, already did the L, A, and D. So this is just 9 factorial over 2 factorial, 2 factorial, which is actually 90,720. All right, when we work that out. And if you're like, how do I do this? I can run through that again. But basically, I like to do control, divide, get the fraction up there, 9, and then down on the right here we got this little factorial button. It's not showing on here. I think it's that one. Whoops. All right, this is swell. 9, and then the factorial button. I can't remember because it's not showing up on here. Yep, there it is. It's that one, I believe. And then we have a 2 factorial times a 2 factorial. Guys, I'm not putting the factorials in there in the bottom. Why? I know that 2 factorial is 2 times 1. I could have just put a 4 on the bottom because that's the same thing. But be careful. Know your properties with those factorials. So 90,720. All right, then the last one on this page here, or or second to last one, I guess. I've got 11 golfers on the junior varsity golf team. 7 golfers compete in a match. 2 of the slots are filled with the best scores from the previous match. How many possibilities are there for the remaining slots? So I have 11 golfers, right? Well, when they compete, 2 of them are going to be the best. So out of those 11, I actually have only 9 people left. So really, I'm picking from 9 people. And how many am I picking? I'm picking 5. Because 7 golfers compete in a match. I already have 2 qualified. So out of the 11, I take away the 2 that are already playing. So really, I'm looking at 9 kids. And I'm saying, all right, out of these 9, I need to pick 5 to fill the remaining 5 spots. All right, well, what am I doing? In golf, and if you don't know this, that's okay. We're just trying a problem here. But in golf, we just have 7 people compete. It doesn't matter what order you compete in. So you're just like going out there as a team. So this is a combination problem. There are 9 that I'm thinking about, 5 that I'm choosing. Okay, and that comes out to 126 different teams. All right, look at this one now. Students were told to make a code name for grade posting. They could either make a code name with a consonant first and a vowel second, and they're saying Y is a consonant here. Consonant, sorry. Okay. Or a code name using any letter first and 1 digit, 0 to 9. All right, so let's think about this, really break this down. The first thing they could do, because it says they could either make a code name. Consonant first, so right away we go here. All right, so consonants, 26 letters in the alphabet, but the vowels are A, E, I, O, and U. Okay, so that's 5. Y is considered a consonant here, so we have 21 choices for that first one. Okay, consonant first, vowel second. So we're going to multiply this by the vowels. Well, the vowels are A, E, I, O, U, which is 5. All right, so what do we got? We got actually 105 possibilities there. Or, so they got 105 to choose from there. Or, so you're going to add the other one. So using code name using any letter first. All right, so here we go. Any letter would now be 26 times 1 digit second. So 0 to 9, that's actually 10 digits. And then that's going to be 260 possibilities there. But they can choose from these or they can choose from those. So that's why we add those together and we get a grand total of 365 possibilities. All right, moving along here to the next page. How many arrangements of answers are possible? On a 10-question test, first 4 questions are true, false. So let's just tackle that right now. First 4 questions. So here's question 1, question 2, question 3, question 4. The key of why I don't go to a permutation here, even though it says like arrangement, I mean this technically is a permutation, but not the way you're thinking, like permutation of, you know, n choose r, is because I can repeat. You can have true every single time. So if repetition is okay, then I want you just to kind of think about them. I got 2 choices here, 2 choices here, 2 choices there, and 2 choices there. First 4 questions, all right? But the rest of the test, so now I have 6 more questions, all right? So 1, 2, 3, 4, 5, 6 more questions, and I have 4 choices for each question. Again, repetition is okay. So essentially, this becomes, 2 to the 4th power is really what this is, 2 to the 4th power times, and then we have 4 to the 6th power. All right, so that's essentially what this problem is. And that comes out to 65,536 different arrangements of answers on the test. All right, now here's the deal. I'm going to take a break to take a bite. You can read through that one to catch up. Looking on here, this is the menu. Okay, so you got to take the time. Hopefully you have that in front of you. But if you look through that menu, basically you have 6 appetizers to choose from. Okay, and the deal is here, most people kind of like these ones. you're picking one of everything. So when you look on the menu, there are 6 appetizers to choose from. And then you go look at the main dishes, 7 main dishes to choose from. And then we have 4 sauces. And then we have 6 sides. Now there was more than that, but I can't remember what I said in here. I'm not in the mood for shrimp. I'm too cheap to pay for anything that's not included. So that really came into how I came up with those choices. But you do get 6 times 7 times 4 times 6. You're getting one of everything. That's the multiplication principle of counting. So it'll be 1,008 for the answer there. All right, moving on to the next one. During trials of a new drug intended to reduce the heart attack, we got this data. But they're asking, what is the possibility that an adult male using the drug will not experience nausea? Not experience nausea. Okay? So what do we got? We got adverse reactions among 800 adult male trial members. Okay? So looking through here, 800 people took it, right? So out of 800, how many got heartburn? How many got a headache? How many got dizziness and all that? So here's the deal. Probably the easiest way to do this one is to be like, all right, well, let's look at the nausea. They're telling me 26. So 26 out of 800 actually experienced nausea. Well, that means that if that's the probability of nausea, then we would do 1 minus that to actually get the probability of not nausea. So that means, and if you just think about the numerator, it makes sense. It's really 800 minus 26. We get 774 people that did not experience nausea, but that's out of 800. Okay, so you can do that there, and you can leave it as a fraction. It reduces to 387 over 400, or you can go to a decimal. That's fine for probability. But that's the idea. Sometimes to get the not one, it's easier just to think about what did happen and then do 1 minus that. All right, number 21 here, getting towards the end here. 2 fair-sided dice are rolled. What is the probability that the sum of the 2 numbers will be 4? Well, really what we could do is we could list out, I want to make sense of this, we could list out all of the possibilities. 1, 1, 1, 2, 1, 3, and we could keep doing this. Guess what? There would be 36 possibilities because we have 6 possibilities times 6 possibilities. We have 36 possibilities. Well, how many of those 36 will actually have successes? And what we're saying is the sum of the 2 numbers is 4. So list out the successes, 1 and 3, 2 and 2, 3 and 1. And if you list out all the possibilities, you'll realize 2 and 2, you don't switch it and get another 2 and 2. It's just one scenario of the 36. Okay? And again, I really want to make sense of this. These are all the possibilities for the first number. But after that, you will get 2, 3, 4, 5, 6. You're going to get 1, 2, 3, 4, 5, 6. If you do this, that's 6 of the possibilities. Do it again, 6 more. 36 possibilities. But there's only one possibility where there's a 2, 2. We have a 1, 3, and then down here we have a 3, 1, so that's why those are reversed, but this is it. There's no more sums of 4. So basically I have 3 successes here. I have 3 successes out of 36 possibilities. And then obviously when I take a 3 out, I have a 1 out of 12 probability. Okay. All right, next one, just think about the bag. The bag has 5 reds, 4 blues, 6. What's the total number that are in the bag? That's how I like to think about it. 5 plus 4 is 9, plus 6, we have 15 marbles in the bag. And just think, how many are successful? Well, we're going to choose 1 marble. It can't be red. Okay, so these are all gone. Can't be red. Okay, not red. That's it, just not red. Okay, so that leaves me with 6 plus 4, or 10 successes based on what it's saying. Okay, so I just reduced that, and obviously I have a 2/3 probability. Lottery game has balls numbers 1 through 23. What is the probability of selecting an even numbered ball or a 10? Be very careful here. Even numbered ball or a 10. You just need to be careful because the 10 is already even. So what we're getting at here, and we did this one in class as well, I believe, on the worksheet. I'm going to list these out, so it'll take me a second, but I want to prove my point. All right, so here's the deal. What is the probability of selecting an even numbered ball? Well, how many are there? Let's see. 1 success, 2 success, 3 success, 4, 5, 6, 7, 8, 9, 10. I have 11 successes out of 23 balls. So I have 11 successes out of 23. But you say, oh wait, the ball could be a 10 too. But I already counted that one. So some people are going to be like, all right, I got 11 successes. Oh, but I got that 10, so I got 12 successes. The 10 is one physical ball. That's it. So you don't add anything more that's already been accounted for. So you need to be careful. There are only 11 successful numbers that will fit this out of 23 possibilities in there. Okay? And some people get a little bit too high on that number because they don't account for the numbers that are really in the intersection of the two sets. All right, survey of pre-calculus. If you start reading through these ones, you're going to be like, all right, well, what's that mean? Basically, you got to look at, again, it's really back to number 23. It's what has been counted twice. So the counting principle basically says, and it works with probabilities too, you take the probability of event A happening, add to that the probability of event B happening, but subtract the probability of A and B happening, and that will equal the probability of A or B happening. Okay, so if we look at this, probability of a student going on a vacation for spring break was 0.56. So that's one thing. All right, I'm going to spring break, 0.56. Okay, 56% chance of a kid going somewhere on a vacation for spring break. Probability of a student going on a vacation for either spring break or the summer is 0.85. So that's over here. So there's an 85% chance of them doing spring break or summer. Okay? And then the probability of a student going on a vacation for spring break and summer is 0.3. So that's actually right here. And then if we just put in here plus the probability of what would B be here, going on a vacation for the summer. So basically that is the counting principle. A single plus single minus intersection equals the union. And then when you actually go through, I'm not going to show all of my work here. You can add the 0.3, subtract the 0.6. You're going to get the probability of B happening, which is student on a vacation for the summer, coming out to 0.59. All right, and that's exactly how you do that problem. Just be careful not to just add two things together all the time. You got to remember about subtracting the intersection between those two. Okay, I hope this helped. The only thing that I thought maybe we should go back to discuss real quick would be just back to this question 15 right here. I just really want you to relay that to the quiz we did and some of the problems in class. This is like if you had scrunchies. All right, if a girl had 3 red scrunchies and then she had 2 green scrunchies and then 1 blue scrunchie. There's the visual. Well, she's got 6 scrunchies in total. Well, that doesn't mean that we can arrange those in 6 factorial ways, because if I switch this red with this red, that's the exact same thing as what you're looking at right now. It's not a different possibility, different arrangement. So 6 factorial will give us a number too high. So again, just like the Cleveland problem, these type, you got to divide out the repetition. So I would divide out the 3 factorial, the 2 factorial, and you could write 1 factorial, but it's not going to change anything. So then you would evaluate that to know how many different ways you can arrange those. Okay, so when you have the arrangement and there's non-distinct items, like some of them are the same, you got to be careful for those. Okay, look back all the review and all that, and hopefully you're in a better spot now after watching the video.